Welcome to MRInotes.com for more MRI physics. Today's topic will be diffusion MRI. And diffusion MRI is very interesting because it's not just giving us anatomical images. The images are telling us about the diffusion of water in tissue. So what we have is this very low-level molecular process, diffusion, which we managed to make visible in MR images, which is really pretty amazing. Not only is it amazing, but it's also very useful in a number of clinical applications. So what we will do here is learn a little bit about what diffusion is, how MR diffusion imaging works, and we look at some of the different types of diffusion imaging that you may come across. Okay, so to begin at the beginning, we can't talk about diffusion without mentioning Robert Brown. He carried out a famous experiment which you may well have replicated yourself in school or in college. What he did was he scattered some pollen grains on the surface of water and he observed the pollen through a microscope. What he saw was that the pollen grains were in a state of constant motion. Now, anyone else would think, okay, well, the pollen grains must be alive, and that's the explanation, and leave it at that. But what Brown did was he repeated the experiment, this time with some dust, which clearly isn't alive, and he saw the same effect. This effect became known as Brownian motion, and ultimately it was shown that the reason for the motion had nothing to do with the pollen or nothing to do with the dust. The reason we're seeing this movement is because the water molecules themselves are in a state of constant motion, and as the water molecules move, they jostle the dust or the pollen grains or whatever is on the surface, and the underlying motion becomes apparent. And this constant movement of the molecules in a liquid or in a gas gives rise to diffusion. Okay, so let's think a little bit more about diffusion just to get a handle on some of the underlying concepts. So we're going to imagine we can do better than Robert and that we can actually look at individual water molecules. So we're going to take the case called free diffusion. Free diffusion is the idea where you're looking at water molecules, say in a glass or a drop of water, where there's no real restriction on their movement one way or another. So what we're going to do is we're just going to let the molecules diffuse for a period of time, and then we will stop and see what has happened. Okay, and the water molecules have diffused. So the yellow cross marks the starting point in each case, and then they've moved a certain amount indicated by the line here. So they've all moved different random amounts. Now, a basic measure you might want to get is, well, how much diffusion is happening here? How can we get a measure of how freely or how far molecules diffuse? And would it be different, say, if you looked in water in a pot of honey compared to water in a glass of water? Okay, so one way we could get a measure is consider, well, how far have the molecules moved? So we would think about the displacement, the length of these lines here. And if we're going to take that imaginary measurement of how far have the molecules moved or diffused, well, then obviously we need to say, well, what direction are we measuring the movement in? So let's say we take this direction as indicated by the arrow. The molecules are allowed to diffuse, and then what we are measuring is the component of motion of the molecules in our direction of interest. So for example, in this case, we're interested in the up-down direction. So what we're interested in is these red vectors, how much or how far the molecules have moved in that particular direction. Okay, or maybe we're interested in some other direction. It's the same idea. If we specify a particular direction, we're measuring diffusion in that particular direction. Okay, now how do we get a number from that? So say again we're interested in this direction. This particular molecule has moved this far, this one this far is indicated by the red vector, and so on and so on. And maybe we have a magic submicron ruler that we can measure these displacements in. So we add this to this to this, and we get an average, and that gives us an idea of the degree of diffusion. Now you can maybe see a difficulty with that. This has moved in a certain direction. This one has moved in the opposite direction. So if we average the two of these, we're kind of cancelling them out. So to get rid of that problem, what you would use is a root mean square measure of displacement. What does that mean? It means you take the individual measurements, you square them, that gets rid of the minus sign problem. Then you get the mean to get an average sense of the degree of displacement. Then you take the root of that value to get rid of the original squaring effect you did. Okay, so in a way it's just a clever trick, but what it does is it provides you with an overall average sense of how much displacement is happening here. Okay, now will you be taking these kind of measurements in MRI imaging? No, definitely not. We're not really that interested in the actual values of RMS displacement, but we still need to have an understanding that different tissues and different materials are going to show different degrees of diffusion. So what does different degrees of diffusion mean, and how can we get a handle on that? Well, again, think about our experiment here and say we could measure the displacement of millions and millions of individual molecules and then plot their probability. What we would get is, for a homogeneous medium, we would get a Gaussian distribution like this. So this plot is showing displacement. So this is how far the individual molecule has displaced in a particular direction. And here we have the probability, and it's showing our classic Gaussian shape. So what's controlling that shape? Well, first of all, the longer that you observe the diffusion for, well, then obviously the further the molecules are going to diffuse. So if we have a longer diffusion time or observation time, then we're going to get a broader distribution. So if our diffusion time goes up, our Gaussian curve is going to flatten out. So in other words, more molecules are going to have gone further. You can see the mean displacement is always zero, and the root mean square displacement, mathematically that works out to be the same as the standard deviation of the displacement. Okay, so hopefully that makes sense. The longer you look, or the longer the diffusion time, the more diffusion you will see. The second factor that influences the diffusion is the diffusion coefficient. So this is a measure of how much diffusion you expect to see in a given tissue or material. So as the diffusion coefficient goes up, the amount of diffusion increases. So in other words, you would expect the root mean square displacement to go up. You would expect molecules to diffuse further in a given time period. Okay, so those two factors, the diffusion time and the diffusion coefficient, are very simply related to the root mean square displacement by a simple formula. We don't really need to worry about that formula. It's really just to remember that we will have more diffusion if the diffusion coefficient for the tissue is higher, or if we observe for longer if the diffusion time is longer. The units for diffusion coefficients are pretty strange, millimeters squared per second. Now, again, in routine imaging, you're not really that worried about the actual values of the diffusion coefficients. It's more about understanding that different tissues relatively have different diffusion coefficients. Maybe if you were doing research on the specific diffusion characteristics of different tissues, then yes, diffusion coefficient would become important. But normally we're not really that worried about the actual numbers involved. Also, the Gaussian distribution here is strictly for a specific case of a very homogeneous medium. You'll be glad to know that's the end of the background physics. Now we're going to look at how does MR diffusion actually work. The trick behind it all is something called bipolar gradients. And the bipolar gradients are going to be used to make the sequence sensitive to diffusion in some direction. If we're interested in diffusion in the x direction, we will use an x direction bipolar gradient. If we're interested in diffusion in the y direction, we will use a y gradient, and so on. Okay, now we're going to see how this works now. We're going to illustrate it using an example of just 3 spins. So what we're showing here are 3 spins at slightly different locations. The yellow arrows are meant to show the transverse component for those spins. Obviously that would be waxing and waning in the real world, but we're just showing it constant for simplicity here. So we've got 3 fixed spins. They're slightly different locations. They're all experiencing whatever the background field is, the V0 field, whether that's 1.5t or 3t. And because of that, they were all processed at the same frequency. So we can see they're all processing, all 3 of them are processing at the same frequency and are in step with one another. Okay? So when we switch on a bipolar gradient, what do we expect to happen to these spins? So remember, what a bipolar gradient will do is it's going to change the B field here. So field spins at different locations in the gradient will experience either weaker or stronger fields. So let's put on a bipolar gradient. So we switch it on. It switches on. So we've got a stronger field at one side and weaker field at the other side, and then it reverses. Okay. So let's repeat that because it happens fairly quickly. So repeat that. So spin over here, experience a higher gradient, so it goes faster. Then it experiences a lower gradient, so it goes slower. Okay. Now, if you look, you'll see the net result on these spins is, well, not very much, because a spin will speed up during one phase of the gradient, but it slows down by an equal and opposite amount during the second phase of the bipolar gradient. So for stationary spins, this bipolar gradient, it doesn't really have much effect. Okay? After the bipolar gradient, the spins look more or less like they did prior to the gradient. They're still in step with one another when we're talking about the transverse component of those spins. Okay? Okay. Now, what's going to be different is when we are looking at a moving or a diffusing spin. Okay, so now we're going to introduce a diffusing spin into consideration and see what happens when we apply this bipolar gradient. So this spin moving around here is meant to represent a diffusing spin. So it might be associated with a water molecule that's diffusing in tissue. So we're going to do the same thing. We'll apply a bipolar gradient. Initially, you can see that the transverse component in the spin is in step with the other stationary spins, but we'll see what happens when the gradient is applied. So we apply the gradient, and the moving spin is going to experience a speed up and a slow down, but because it's moving, it's going to be in different locations during those 2 phases of the bipolar gradient. So it doesn't get an equal speed up and slow down, so its phase is going to change. So you can see its phase has changed relative to these these stationary spins. Now you can imagine if we have many diffusing spins, then they are going to fall out of step with one another because of this bipolar gradient. So the more diffusing spins you have, the more those spins are going to be, the transverse components are going to be out of step because of the bipolar gradient. And if they're more out of step, that means we're going to have reduced signal from those diffusing spins. So what we've done is, by introducing a bipolar gradient, we've made the sequence sensitive to diffusion in such a way that the more diffusion we have in tissue, the less signal we're going to get. So in regions that have a lot of diffusion happening, then we're going to get a reduced signal. We're going to get a hypointense signal because of this diffusion sensitizing bipolar gradient that we're using. Okay, so here is the full diffusion imaging sequence. The base sequence here is a spin echo EPI sequence, which would be typical for a diffusion sequence. So we're showing the full timing diagram here. It looks a little bit scary, I have to admit, so let's just work through it. So as usual, the timing diagram is showing the radio frequency transmitter, the signal received, and the three gradients X, Y, and Z. Okay, so the pink purple part of the signal, that's just a standard EPI sequence. The yellow part is the bipolar gradients, which we'll come to in a second. Okay, so to work through each of them, on the radio frequency transmitter, we've got a 90-degree pulse, 180-degree pulse. On the signal, we can see these multiple echoes coming back. On GZ, we're assuming it's a transverse slice, so GZ is acting as slice select. It's on during radio frequency transmission, as you'd expect. GX is the frequency encode gradient in this case. You can see it's switching rapidly, and that rapid switching is generating these gradient echoes that ultimately go to fill K space and form the image. And then our phase encoding, we're just showing this blipped type phase encoding, which is moving us from line to line. Okay. Now, it doesn't really matter if you don't get all that or don't remember it all. The important bit that we're showing from the point of view of diffusion imaging is these yellow bipolar gradients. So remember, we said that if we are interested in diffusion in the Z direction, we would use the Z gradient. So that's what we are doing here. But equally, it could be X or Y. So we can see here we've indicated the direction of diffusion that the sequence will be sensitive to, and it is in the Z direction. Okay, so these are our bipolar gradients. So you look at these and you think, okay, that doesn't look very bipolar because they're on in the same sense. Would you not expect one of these to be negative? Well, yes, you would normally, but because we have a 180-degree pulse here, the sense of everything is effectively reversed. So that's why we are seeing the bipolar gradients looking like they have the same direction in both phases. Okay, so if we were interested in a diffusion in some other direction, we could, instead of using Z, we could use Y, and that would produce a sequence like this, which is now sensitive to diffusion in the Y direction. Or we could use X, and in that case, the sequence will be sensitive to left-right diffusion. And we can see now the bipolar gradients are on the X gradient. And if we were interested in some oblique direction, we'd simply use a combination of the different bipolar gradients. Okay, so the bipolar gradient has introduced this sensitivity to diffusion. But how much sensitivity has it introduced? Is the sequence really sensitive to diffusion, or just a little bit? Well, what determines that is the strength and duration of the bipolar gradient. So that's the low-level physicsy thing that's going to determine how sensitive the sequence is to diffusion. Okay. Now, control of those factors and control of the degree of sensitivity to diffusion is set by something called the B-value. And the B-value is something you can set at the console. If you set a larger B-value, that makes the sequence more sensitive to diffusion, and vice versa. Now, at a low level, what the B-value is doing is influencing those bipolar gradients. But for practical purposes, the important thing about it is a measure of how sensitive the sequence is going to be to diffusion. Okay, so let's talk about the B-value in more detail. And really all revolves around this graph shown here. What we're showing here is the signal intensity from a given voxel for a given diffusion coefficient. Okay, so remember, the diffusion coefficient is a measure of the degree of diffusion in that voxel. It's not something we can control. It's a real world thing that's out there. And we said that the more diffusion we see, the lower the signal is going to be. So this graph makes sense from that point of view. At a higher diffusion coefficient, the signal is going to drop. In other words, the pixel or the voxel is going to show darker. Okay, and it's not a linear relationship. It's kind of an exponential curve. Okay. Now, what we're showing here is the signal level versus diffusion for a given B value. So for a given setting that you have set up at the console that's saying the sequence is going to be this sensitive to diffusion. Okay, so what is going to change if we change either the diffusion coefficient or the B value? So if we change the diffusion coefficient, so we increase the diffusion coefficient, the signal level is going to drop. So in other words, the more diffusion in a voxel, the lower the signal we expect. And the more restricted the diffusion, right down to the point where there's no diffusion at all, we expect the signal to be higher. Okay? Okay, now say we set a different B value. If we set a B value of 0 to take one extreme, that means the sequence has no sensitivity at all to diffusion. So it doesn't matter what the diffusion coefficient is, we're just going to get a certain signal level S0, and that value S0 is just going to depend on the weighting for the sequence and the characteristics of that particular voxel. Okay? And as we increase the B value, what we see is we get increasing sensitivity to diffusion. So we get a greater drop as the diffusion coefficient goes up for larger B values compared to smaller B values. Okay, so that's the general relationship. And that's all captured in this formula here. Now again, if you like formulas, that's fine. If you don't, it doesn't matter. All the formula is saying is that the signal that we expect to get is influenced by three different things. The degree of diffusion that's happening in the voxel, the sensitivity of the sequence to diffusion, which is determined by our B value, and S0, the signal that you would expect to get anyway in the absence of any sensitivity to diffusion. Okay? So a major application of diffusion-weighted imaging is in the detection of cerebral ischemia. The idea here is that ischemic regions will show reduced diffusion. And reduced diffusion means less signal loss on a diffusion-weighted image. So in other words, ischemic regions will show hyperintense on a diffusion-weighted image. So here we have an example of diffusion-weighted imaging with three different B values where the elevated intensity is consistent with ischemia. So which direction of diffusion are these images showing? Remember we said that the bipolar gradient can be x, y, or z, or some combination of x, y, and z to give you sensitivity to diffusion in a particular direction. Well, if you're looking at images that are called isotropic diffusion-weighted images, what's actually happened is the machine has generated a diffusion-weighted image for the x direction, for the y direction, and for the z direction, and then has combined them before it presents them to you to give you an averaged diffusion-weighted image, which is called the isotropic diffusion-weighted image. And because of that averaging, the dependence on direction has been removed and the intensity values are related to diffusion independent of direction. Okay, so let's think a little bit more about what we are seeing in these images. So we know that restricted diffusion in a diffusion-weighted image will result in a hyperintense region. So when we see a hyperintense region, does that mean for sure, yes, there's restricted diffusion in that region? Well, no, because the reasons for the region being hyperintense might well be that the diffusion is restricted, but it might also just be that that region produces a strong signal because maybe it's got a long T2. So diffusion-weighted imaging is showing diffusion, yeah, for sure, but it's not just showing diffusion. So to move up a gear and get images that are really just sensitive to diffusion, we have to change things a little and implement what's called an ADC, or an apparent diffusion coefficient image. So to fully understand how an ADC image works, we need to go back to this little formula, if you remember that one, which is showing us what the signal level from given voxel is going to be in a diffusion-weighted image. Okay. Now, you will remember that that signal level depended on three things. It depended on D, the diffusion coefficient. That's the thing we're really interested in, the unknown value. It depends on B, the B value that you've set which determines how sensitive the sequence is to diffusion, and it depends on S0, which is the signal you'll get from the voxel in the absence of any sensitivity to diffusion. Okay, and it's that S0 which is causing us the problem, because that S0 isn't dependent on diffusion, it's just whatever the signal you would normally get. And that is going to result in what's called T2 shine through, which means that for long T2 values, you're going to get elevated S0 values. In other words, you get strong signal from that voxel. And that strong signal in a DWI, diffusion weighted image sequence, can be confused with restricted diffusion. Okay, so what we'd really like to get is to get closer to an image that just reflects the diffusion coefficient, that doesn't have this dependence on other factors, that gets rid of the S0 dependence, that gets rid of the T2 shine through. So what we're going to do is we're going to generate images which are called ADC, or apparent diffusion coefficient images. Now, these depend on a little mathematical trick which involves taking this formula and taking the log of either side. Now, if you're familiar with this kind of thing, it will make absolute sense, and you'll see what's going on. We've got rid of the exponential effectively by doing that. If you're not familiar with this kind of thing, it doesn't matter, because I'm going to explain it now, and it's actually pretty straightforward. What all this shows mathematically is what we're showing here. Okay, so let's ignore the formula and think about what's going on here. Okay, so what is this relationship showing? It's showing the signal level from a voxel here. In other words, how bright it is. Strictly, it's the log of the signal level, but still it's signal level, versus the B value. Okay, now there shouldn't be anything too surprising here, because as the B value goes up, in other words, the sequence gets more sensitive to diffusion, the signal level drops off. Okay, now the useful part of all of this is that the slope of this line is determined by the diffusion coefficient. So if the diffusion coefficient is high, if there's a lot of diffusion in that voxel, the slope of the line is high. If the diffusion coefficient is lower, then the slope is more gentle. Okay? So if we could get the slope of that line, if we could measure it some way, then we would have a measure of the diffusion coefficient, which is really what we're looking for, independent of shine through. Okay? So if we could set things up some way that we could effectively plot this graph for every voxel, then the machine could do all the maths in the background, get a measure of the slope, and therefore get a measure of the diffusion coefficient, and color in the voxel appropriately with a dark level or bright level or whatever. Okay? Okay, so how is an ADC implemented in practice? Well, it's very like a student doing an experiment where they have to collect data and plot a graph. Now, luckily, the machine does all the hard work. We don't have to worry about plotting the graphs. But this is what happens. In an ADC, we are running diffusion-weighted imaging. So the backbone is, as described before, we're running DWI images. The difference is that we will collect a number of DWI images at different B values. So taking an example here, where just as an example, we've run an ADC and it's used 3 different B values. So it's collected DWI images with different B values. What it will do in the analysis is it will move around pixel by pixel, and for every pixel it will effectively, in the computer's mind, it will generate a graph. And the graph will be, as on the previous page, it will be the signal level, or the log of the signal level that was measured versus the B value. So for example, this pixel at this B value is plotted. The intensity of this pixel, the same pixel, at a different B value is plotted, and the intensity of the pixel at another B value is plotted. Okay? Now, we know when they're all joined up together, or we try and plot a line through them, that the slope of that line is a measure of what we're looking for. It's a measure of the amount of diffusion in that pixel. And the final step then is to take a measure of that slope for every pixel as calculated and to plot it as an intensity level in a new image, which is the ADC image. So in the ADC, the intensity of the pixel is related to the apparent diffusion coefficient. So in other words, the more intense the pixel is, the higher the diffusion is in that pixel. So remember, it's going to be the inverse contrast to a DWI. In DWI, hyperintense means restricted diffusion. In ADC, hyperintense means more diffusion. Okay, but the whole reason we've done this is we've generated an ADC so that the image is more directly related to diffusion. It's not going to show that T2 shining through effect. Okay, so to finish, I just want to very briefly discuss another variant of diffusion imaging called diffusion tensor imaging, or DTI. The maths and physics behind this are pretty complicated, so I'm just going to give an abbreviated description of some of the main principles behind it. So first of all, just to describe the difference between isotropic diffusion and anisotropic diffusion. In isotropic diffusion, we're considering that we've got a homogeneous medium and the diffusion is equally likely in any direction. So for any given direction, if we were to plot the root mean square displacement, that plot would show the surface of a sphere. So there's no directional element involved. If the tissue shows more diffusion, it's simply that the radius of that notional sphere is larger. And if the diffusion is lower, it just means that radius is smaller. That's all. But in general, in any given tissue voxel, you may have a preferential direction of diffusion. So this is called anisotropic diffusion. So if we imagine, say, in the brain, if we had a voxel through which a nerve cell was passing, then we would expect that the preferential direction of water diffusion would be along that nerve, for example. Okay. Now, for any given voxel, the anisotropic diffusion in that voxel can be represented by an ellipsoid surface, as shown here. So the idea here is that the surface represents the root mean square diffusion in any given direction. So for example, here we can see that the dominant diffusion direction is in the y direction, with less diffusion in the x and y directions. Now, depending on the contents of that voxel, that ellipsoid could be at any orientation, or it could have any dimensions depending on the degree of diffusion in any particular direction. Now, in diffusion tensor imaging, the MR collects sufficient data that for every voxel it is able to generate or represent the underlying ellipsoid. Okay? Now, we're not going to go into the detail of the physics and the maths of how it does that, but you can see that it's collecting a lot of information that tells you effectively all you need to know about the degree of diffusion and all you need to know about the direction of the diffusion in every voxel. One application of DTI is called tractography. So in tractography, what we're trying to do is plot the pathways of tissue fibers in 3D. And the typical application for this is plotting the pathways of white matter fiber tracks in the brain. So it works by running a DTI acquisition, and that DTI acquisition provides information on dominant direction of diffusion in every voxel in the imaging volume. So essentially that ellipsoid information that we spoke about in the previous slide. And it then runs an algorithm which traces the most likely pathways for the fibers through that imaging data. So what it's trying to do is connect from voxel to voxel following the most likely diffusion path along a tract. Another concept in DTI is fractional anisotropy. So if you're looking at a fractional anisotropy image or an FA image, what the gray levels are telling you is how anisotropic a given pixel is, okay, which sounds pretty confusing, but that really means that if the voxel is if the contents of the voxel are very directed, then that voxel will be highly anisotropic. So for example, again, if there was a fiber tract going through that voxel, you would expect it to be very anisotropic. So on an FA image, it would appear more intense, it would appear hyper-intense. In an FA image, the underlying acquisition will again be a DTI, diffusion tensor image acquisition. The calculation of the FA value for every voxel comes from this extremely scary looking formula, but effectively this formula is working on the DTI data to give every voxel a value between 0 and 1, which represents the degree of anisotropy in that image. So depending on how isotropic or not that voxel is, the value will range somewhere between 0 and 1. You may also see FA images presented with the directional information superimposed in the form of a color map like this, where the color convention is as shown and the dominant direction of the anisotropy will be shown in red, green, or blue. So that's our run through the physics of MRI diffusion imaging completed. I hope you found it useful, and thank you for sticking with it.